All right, everything is set up. We are good to go. Welcome everybody to today's lecture on computer game AI. Last time we have began to look into the notion of Markov chains or models. Both terms again are used interchangeably. And the fundamental aspect behind this idea is basically that we are looking at a set of random variables. Let us denote this set as x subscript t, where this t is supposed to indicate a point in time, and we are interested in discrete time processes, so let's fix this subscript to a natural number, and we are good. And secondly, so we have a set of random variables, which we understand as many random variables, and we are interested in the value of each of them at certain different points in time. One of the xt could be the weather today, xt plus 1 would be the weather tomorrow, xt plus 2 would be the weather 2 days from now, and so on and so forth. So these are random variables that characterize the state of something at a certain point in time. Right? Each of them, this is the second thing we are interested in. Each of those random variables is supposed to take a value in some set S, which we also, for the time being, actually like for throughout this lecture, we'll only look into discrete sets S. So this set S is referred to as the state space, and in that sense each of these random variables which indicate something that is going on at different points in time assumes a state out of this state space. If you remember, we had an example last time where this set S contained 3 elements, and they were called room A, room B, and room C. Right? There was this trivial game map consisting of, say, 3 rooms in a dungeon, and we were observing temporal patterns, basically consisting of sequences of A's and B's and C's. This is a good point for me to already point out that when we look at discrete state spaces like that, we can think of the states in terms of semantic concepts, right? Room A, and we know what room A is. There's a certain mental picture we have if we talk about room A, but as these things are, well, discrete elements in a possibly large set containing only discrete elements, we may also talk about these things in terms of numbers. Right? So, for instance, instead of room A, I could say we have state 1. Instead of room B, we have state 2, and then state 3. This is, of course, not really intuitive when we are talking about states and refer to them by natural numbers, but this will allow us to sort of simplify the mathematical notation. Right? So later on today I will talk about states, state 1, state 2, state 3, but we can always, in our minds, map these state identifiers to something more intuitive. So there's like really no problem here. This is just to say that we have a discrete set of states And we can talk about these states either by their names or by an ordinal number. If you use the numbers, equations get simpler. Now, we then said that these random variables xt form a discrete time Markov chain. Discrete time Markov chain. MC is a very fancy abbreviation for Markov chain. If their joint probability, that is to say, this mathematical construct, x1 all the way up to some, I'll make it like this. Do it like this, x2. Many of them, I actually, here I'm not looking for the last one, could put some xt here, I don't. So if their joint probability, that is, once again, the probability to observe all of them, the first one, the one at the second point in time, the one at the third point in time, to assume each a certain value. How likely is that? Let's say x1 is A, x2 is A, x3 is B, and so on and so forth. This joint probability is supposed to respect the following graphical model, and this is indeed x1, x2, and so on and so forth. So this is the graphical model. These random variables or their joint probability are supposed to respect. If that is the case, we are talking about a discrete space, discrete time Markov chain. Once again, because in this lecture we just focus on discrete state spaces. All of this can be extended to continuous state spaces and even to continuous time. Alas, and that is in a careful sense very straightforward. Alas, things get out of hand in terms of understanding that from an intuitive point of view. So let's just focus on discrete space, discrete time, Markov chains, and indeed for the realm of computer game AI, that is good enough. Okay, two more things. What does it mean to say that the joint distribution respects the graphical model like this? Let me just put one more here. So x3 and like so. This sentence, the joint probability of these random variables indexed by time respects this graphical model, is to say that, so in other words, we know that this joint probability will factor in a certain way, and that is to say that we have here x1, x2, and so on, can be factored as the probability for x1 being in a certain state times the product where t ranges from 2 up to some, given my notation, I'll have to stick with this. So t larger 1, p of xt given xt minus 1. And this is exactly what it means to say that the joint probability respects this graphical model, because we talked about conditional independence and saw that in these head-tail diagrams we have indeed that this random variable is conditionally independent of this random variable given that one. Or, in more intuitive words, the future is independent of the past given the present. And that is at some point we start, so what is the probability for this variable to have some value? This is this factor here, and then we have this factor of conditional probabilities, where the probability for the random variable at time t is only conditioned on the random variable at the previous point in time. It ignores all the history except for the last point in time. And I'll make that more precise once again. So what I just said boils down to this statement, that is that the probability of xt, which we could condition on all the history, so say on xt minus 1, xt minus 2, all the way up to x1, is indeed not dependent on the history, but really it's just given by this expression, the probability of xt conditioned only on the last point in time. So these are three ways of thinking about Markov chains. Right? It really depends on what kind of a text you read. For instance, in mathematical textbooks, they are happy with this one. They don't talk about graphical models and factorizations. This is more what the people in the area of machine learning or data mining do. They like their graphical models, and once they have their graphical models, then we can talk about joint probability respects the model, and then that is of course to say that we have this factorization. The mathematicians are happy with this statement. That's good enough actually. This defines a Markov chain. All right. Yeah, we actually looked into how we may use Markov chains in the context of game AI. We had this example of a game map consisting of 3 distinct rooms, A, B, and C, and sequences of observations of where the opponent was located in room A, room B, or in room C. And then we had 2 models that came out of our heads. Where do they come from? Somebody has to sit down and think, what do we want to represent? And once you have decided that, then you have to think about how do we represent that. So we had 2 models, 2 representations of 2 different behaviors, and we used the idea of Markov chains to compute the probability of observing a certain sequence of states under the one model and to observe that sequence of states under the other model. And the one that was more likely is then likely to be the one that is more correct. And so we can use that to infer what is going on from sequences of observations, and that is different to what we have been doing up until then, where all our decisions, when we talked about behavior programming, were based on what is going on right now. That was the first time we saw that it's indeed quite easily possible to include temporal context into reasoning as to what is going on in the game world. Now, before we continue, let us also recall that these expressions I've been writing down so generously, so this xt, probability of xt given xt minus 1 is but a shorthand for the expression that the probability of the random variable xt assumes a value of I, given that the random variable xt minus 1 assumes a value of j. And whenever you see these things, these expressions, you have to mentally read them like this. This is important because Eventually you get used to that, and then it's natural, but when you are exposed to these kind of techniques for the first time, I found it confusing. I didn't really understand as a student. So mentally you have to map this to this, and because we are lazy, we don't want to write down all of this all the time, we sort of abbreviate it by that. Right. Now that we have reminded ourselves of that, we can think about what it means for a Markov chain to be homogeneous, A or N. A Markov chain is time homogeneous if, let's start with this expression because then we can see it more easily. The probability for the random variable xt, assuming a value of I, given that the predecessor, the previous random variable xt minus 1, had a value of j. If this probability at a certain point in time t, and of course previous point in time t minus 1, is the same as the probability that another random variable xt, say plus delta, assumes a value of I, given that its predecessor xt plus delta minus 1 had a value of j. Last time I wrote this slightly different. It does not really matter. I thought I expose you to different ways of expressing this idea. Once again, what this says is that what really matters is not so much the point in time we are talking about, but the change of state j to I. Right? And if this is exactly as probable at times t minus 1 and t as it is at times t plus delta minus 1 and t plus delta. So sometime else, right? This could be, I don't know, right now, and this could be in a year from now. If the transition from a state j to a state I does not depend on the point in time, then this Markov chain is time homogeneous. But then we can actually, ignore these random variables when we write that down. Because then again, basically, what really is important is the probability of transiting from a state as j to a state as I. But S is a discrete set. So far, elements of S were called room A, room B, room C, but we may as well call them 1, 2, or 3. It's a bit more abstract, but it doesn't matter, because if we know that 1 refers to room A, or it could also be 1 refers to defending the base, 2 refers to rushing towards the enemy, 3 refers to going back to the base. As long as we know what these numbers represent, we can talk about the states in terms of numbers. And so far it's not really apparent why that is interesting to do. Why should we actually do this? Well, because we are lazy. Even this expression, even though it's like considerably less cluttered than this one, is too much for us to write down. And so we call this simply Pij. Right? And that would be difficult if I was room A and J was room B. Then we'd have to write down P room A, room B. Let's stick to numbers here. So this is maybe good to point out once more. This is a property that does not hold for every Markov chain. We can, more generally these transitions could actually depend on the value of t. But if we say they don't, then everything boils down to this. And it's not so much, what's of importance then is not so much what value the state variable at time t has given the value of the state variable at time t minus j. The real important thing is basically how likely is it to transit from j to I. And this can be captured in terms of this notation. Okay, now we have something that has two indices. What does that hint at? We are dealing with a mathematical object that has two subscripts. Have we seen something like that before? I will come back to that. I saw that I'm just ahead of myself. I'll come back to that in a second. If it's only these transitions from one state to the other, we can think of Markov chains in yet another graphical representation. So a homogeneous, discrete space and discrete time Markov chain is completely characterized by the transition probabilities between states. And once we accept that, we know, and like in math textbooks, this is what they do anyway, that we can think about a diagram that contains the different states or different elements in this state space, in this set S, as say vertices of a graph. So we have Sj, Si, what else do we have? Some Sk, and I don't know, some SL. And yeah, you know, from sitting down and thinking about some problem, or somebody models something, says, okay, we have a problem domain where there are 4 different states. You could have called them S1, S2, S3, S4, but in general, you know, there could be more, so some variables here to denote the indices. We have, in this example, 4 different states, and it is likely to transit from state Si to Sj, but it may also be possible to remain in state Si. At the same time, it may be possible to go from state Si to state Sj, then to Si. There might be a probability for self-transitions. It could be possible to transit from Si to Sk, and it could be possible to transit from Sj to Sk. Here we again could have self-transitions. We might have a transition like this, and a transition like that. You know. Note that I left out certain arrows, but that is on purpose. Right? It does not mean that if we are given a discrete set of states, we can reach each state from each other state. So in this example, we, for instance, could not reach state Si from this state SL. And this is a transitional state because there is no self-transition here, so you know, once we reach it, we either go back or continue to Sj. So this is this resembles finite automaton, right? That is indeed what it is. We can, if we want to, I'm careful here, but we can think of Markov chains, time homogeneous, time discrete, state discrete Markov chains, as these finite automata. We have a set of state. We talked about that. We can transit between states. The important thing is I didn't note it here, but we would have these Pij numbers attached to all these edges here. And they are probabilities. So in contrast to a finite state machine, here the transition is somewhat of a thing that depends on chance. It can happen that we transit from this state to that one. It can also happen that we remain in this state. Right. So I'll just put another one. This would be Pjj. Just ever so briefly, we talked about minimizing finite state machines. The fact that this SL is a transient state, we never stay there, but basically go from SK to SL and from SL immediately to SJ or back. That hints at the possibility of removing this state. Right? Because instead of doing this, we could do this immediately. And instead of doing this, we could do this immediately. So if you design these models, if you're ever in the situation that you have to represent some complex temporal process in terms of Markov models, you can also verify if these models are sort of minimal or not. Sometimes there might be a possibility to get rid of certain states by introducing other errors. Maybe that is something that might be of interest. That is called lumping of Markov chains. We are not going to look into that. That is far beyond what we can do. But to make a long story short, you can simplify these models if need be. Now here's the thing I've been asking about. We note that I should probably put a warning sign in front of it because this is I have to tell you, otherwise you might run into troubles later on in your life. Note, when I write Pij, then I am referring to the probability of transiting from state J to state I. So this is the probability of transition from Sj to Si. And I am stressing that because the literature does it the other way around. They put the J first and the I last. And that leads to, let me point it out. The literature usually does it the other way around. That is Pji to indicate the probability of transiting from J to I. Right, so this is probably because this is written left to right. But I, third time, do it like this. Right, so you have to be aware of that. And I have a reason for doing this. And the reason is as follows. So we have something with two indices. What is that? It's a matrix. numbers, pi, the numbers, these are all numbers, right? All numbers between 0 and 1, they are probabilities, but we have lots of them, and depending on what states we are talking about, there is a number. We have lots of numbers. These numbers form a matrix. In a sense, obviously, right? Because it's a collection of numbers with two indices. What a matrix does. And let me call it matrix P. And if we have m different states in the set S, then this is a matrix of dimensions m by m, where this m denotes the number of elements in S. So here is how this matrix looks like. Matrix P is given by the way I am doing it. P11 all the way up to some P1m. And here we have, of course, P21, and this goes down to Pm1. And here's like P2m, and here's Pmm. This is how this matrix looks like. No big deal. Once again, where? Well, these are probabilities, right? So each of the entries is a probability. Each of these entries is a number between 0 and 1. So basically they are greater or equal than 0. The second thing with respect to them being probabilities is that if we sum these numbers in every column, so we sum over all rows I, Pi in column J, then this has to add to 1. Now, it can happen. Once again, each of these numbers has to be greater or equal than 0. And every column has to sum to 1. That can, for instance, be the case that, I don't know, make it as, let's introduce a new one, as m here. Now, once we have somehow reached state Sm, then the probability of transiting from Sm to Sm is 1. So in the corresponding column, the column that would indicate state Sm, the row, the diagonal element would be 1. So the probability here, P, M, M is 1. Everything else is 0. This is what it means when I do not draw any arrows, then that means the corresponding transition probability is 0. Now, what does that mean? We have one element that is 1, and m minus 1 elements that are 0. If we sum that together, then indeed it is 1. Well, we are good. Right? If we have a couple of arrows going out of a state, well, then the probabilities attached to these arrows have to sum to 1. Right. Let's verify if that makes sense to require that this sums to 1. We don't need the diagram anymore, so I'll do it here. So let me call this one star. Star because, let's ever so briefly verify that this makes sense. Well, so what we have written there is sum over I Pij. But we have agreed that this Pij is just a shorthand for sum over I probability of transiting from state Sj to state Si. That, no big deal here. Now we apply Bayes' theorem or the product rule of probability, and then we can write this expression here, sum over all the I, as the joint probability of Si and Sj divided by the probability of Sj, whatever that is. Does not really occur here in our context, but algebraically that is what we have. Now, this one does not depend on the summation in xi. I will pull it out of the summation, so 1 over probability of Sj times the sum, the joint probability Si and Sj. Well, we spent quite some time on establishing that if we marginalize over one of these two variables, the result is basically the probability of the other variable. So we have 1 over probability of Sj times the probability of Sj, and that is of course 1. So that works. All right. If we look into whether or not this is true, then very simple arguments establish that indeed that is the case, and more intuitively. So we have a state, right, one of these vertices, and there are other vertices in this graph and arrows between these things. And there might also be self-transitions. Well, of course, it has to be like that if we are in a certain state at a certain point in time. We either remain in that state or we, at the next point in time, are in one of the other states. So these probabilities really have to add to 1, like intuitively. Okay? But now, if we do it like this, we just established that if we sum each column, we fix sum j somewhere here, and sum over all the rows in that column, and that adds to 1. So we have established that P is a column stochastic matrix. And this is just a fancy way of saying that all the elements in matrix P are larger or equal than 0, and that each of its columns sums to 1. If both these things are given, then we are talking about a column stochastic matrix. And now this is why I write the PIJs like this, right? Because I like my matrices to be column matrices, but in the literature on Markov chains, you usually find them to be row stochastic. And then you can do linear algebra with row matrices, but then, so the basic difference is if you have some probability vector in the literature, typically this is done like so. You have the vector times the matrix, because the matrix is a row matrix, but we don't do this. I like my matrices to be column matrices, so this is how we would do it. Row matrices are an abomination of nature, and they should not be tolerated, and I really don't understand why everybody does. But you have to know that this is my personal opinion. So if you find all this sort of flipped if you read a book, don't be surprised. That does not really make a difference. Technically, that is exactly identical. But I don't like row vectors being multiplied with matrices. I like matrices being multiplied to column vectors. So we had to switch the meaning of Pij. But we can do that. Okay. Yeah, I'm at a crossroad here right now. This is all candy and apple juice so far. We have just assumed that somebody has given us a Markov model, for instance, about what it means to patrol a certain area of a map or to guard a treasure, right? Somebody has provided us with two Markov models containing states, same kind of states actually in both models, but different transition probabilities. Once we have these models, we can use them to decide what is going on given a certain sequence of observations of where the player is. The question, of course, would be how to actually set or come up with these probabilities that are attached to these transition arrows. Where do they come from? Right. Well, they can be learned. They can be learned. And we could do that using maximum likelihood. And I would love to do this, but so I'll prepare lecture notes which I will upload to the website, and you can read it there because it will take too much time. I don't know where we lost so much time already. Let's ignore that, but let me tell you that there are ways of how to determine or estimate the values for all these numbers Pij from data. Right? If you are given a lot of sequences where somebody, for instance, has told a human player to play the game and guard the treasure. Right? And then we have sort of a recording of how often did the human player guarding the treasure go from room B to room A, or stayed in room B or went to room C. We have recordings which contain these sequences, and based on these recordings we could then use statistical parameter estimation techniques to infer the best values for these transition probabilities. Right? I'll upload it to the web page. We can use machine learning to estimate the model parameters. But in the interest of time, we will ignore that and move on to what we are actually interested in. That is the idea of hidden Markov models. Or, as everybody likes to call them, HMMs. And to begin our study of that, I have to point out that sometimes, and when I say sometimes, I really mean often, we cannot observe the state variables, these xt in the set of states directly, but instead of being able of observing them directly, we have only, but have only indirect observations, and I'll call them vector OT, I don't know, in some set O of observations, and for instance that could indeed be a set of d-dimensional real vectors, something else. So this is the crucial observation, and of course it is not at all clear what I want to say by this, so we have to look into an example, right? But for what we have been doing so far, when we talked about Markov chains, we said there are different states a game agent can be in, and our canonical example was a state being a room, which is great because an agent can be in a room. We can actually observe that right now the agent is in room A, or it was in room B at the previous point in time, and before that it was also in B, and so sort of the notion of a room being a state an agent can be in is very natural, and that makes a lot of sense. So what or why would I claim or say that we cannot always observe the state an agent is in, but have only access to something else? It is the case. Let's see why that is the case. And actually in the last project you have been dealing with exactly this problem. In a different manner though, but. So here is an example. Instead of assuming 3 distinct rooms, let us assume just one huge area, right? So to make sure that there is no such thing as discrete subdivision of the map we are talking about. And at some point on this map there is a treasure, and at some other point, I don't know, make it here, there is a health package. Health pack, right? And now we are a human player, and we observe another player, say a computer-controlled non-player character, doing this. So we somehow have entered the map, and we observe the other player to, you know, wonder about this treasure. And then, for whatever reason, at some point in time, we see this, and then we see this. How would you explain these observations? What is going on here?
Maybe he's fighting somebody.
Yeah. What would it mean to say it's going up and down in the vicinity of that treasure? What does that probably indicate? It's guarding the treasure, right? So when he's walking up and down, it is in a state which we have just called guarding the treasure. Okay, yeah, and then maybe it's engaged in a fight, who knows? But at some point in time, we see this. What is that? Running for health, right? And then we see this. What is that? Going back to duty, right? Going back to guarding the treasure. This is very, very interesting if you think of it. we look at something like that. This is of course just an abstract representation. You know, this could be a scene that unfolds in front of our eyes while we are playing the game. We have entered an area. We see a character going up and down, then run over here, then run back, go up and down. When we observe something like that, our brain has a tendency to try to summarize what is going on. Right? And this sort of observation of the character going up and down about here in the vicinity of the treasure, we would summarize that by, say, guarding the treasure. And then we observe something else, which we call, oh, now it is running for health. And then we observe something else, which we call, now it's going back. 3 different states. Can we see them directly? No, we can't. Right? They are not there. Given what we see about the scene and what is going on, we do not see the internal states of the agent. We see what the agent is doing, but we don't see the states it is in. But from what it is doing, we infer that, oh, right now it is in the state of guarding the treasure, and right now it is in the state of running for health, and right now it is in the state of going back to its guarding duty. And this is what I mean by sometimes, in parentheses often, or usually, we don't see the states. What we see is something else, and maybe from that something else we can infer the states. So here in our case, I just write it down, the states, we just sort of did it already, could be called guard, guard treasure, treasure, run for health, and return, I don't know, to duty. This is of course a choice of ours to define or to state or to say that 3 different states are enough to abstractly carry on what is abstractly characterize what is going on here. Maybe we could have, I don't know, introduced 5 of these states. Nobody would have prevented us from doing so. But let's for the sake of simplicity say 3 of them are enough, right? And obviously it looks as if it is enough. We have going up and down here, which we call guarding, then we have running over here, which we call run for health, and running back, which we call return to duty. Yeah, so 3 different states which have a semantic meaning to us, but we can as well call them 1, 2, and 3, right? As long as we know that 1 refers to guarding the treasure, 2 refers to running for health, and 3 refers to returning back. So therefore, it's another discrete set of states which abstractly we can talk about as 3 different states, and let's assign just numbers to them. Of course, when we do that, keep in mind that each of these numbers actually has an interpretation to us. Yeah, so then what are the observations? For instance, what we could think of the observations would be like these tiny arrows where it goes from this location to that location. This is a vector now, right? So this could be one of these observation vectors at time t would be such an arrow. And of course, in this example here, each of these arrows is a 2-dimensional vector, but of course in more realistic settings, these observations can be higher dimensional, more rich in meaning. You can take it from here. This is, again, just a contrived example, right? Yeah, so this is an example. This is an example of a setting where it may be interesting to us to infer a state an opponent is in, because once we know that, we can do something about this, but we do not know what state it is in, but what we know is what it is doing. Right? And from what it is doing, we have to infer the state. So we have, this is if you wish, reducing the complexity. We have lots of things going on, and we try to interpret what is going on in terms of three concepts, three elementary behaviors, right? So we reduce complexity by going from these observations to these states, and if we can infer a state an opponent is in, we might be able to do something. And hidden Markov models are used for inference, in situations like these. Now, then, in how far are they different from Markov chains? Well, obviously, in contrast to the Markov chains, where we may, which we use when we can observe the states directly, which we can if the states are just being in a room or whether it's sunny or whatever. Like if that is actually the state, sort of is already the observation we have, that is good. But here, again, observations are different from internal states. So how is that different from the Markov chains we have been looking at? Well, obviously there are two sets of random variables now. Two sets of random variables. We have these state variables, x1, x2. Let's fix them. I don't know, there's just n possible state variables. And they assume values in this set of states, and we, implicitly or more or less explicitly, quite some time today already said, we can think of this set of states as a collection of numbers 1, 2, 3, all the way up to some n, right? Of course, when we do this, this is a mathematical abstraction. These numbers mean something, but let's just say a state is a number. You are in state 1, and then you transit to state 3, and from there to state 25, and then back to state 1. Whatever state 1, 3, or 25 refer to, we observe these, we have these states. And then the second set of random variables, let's call them O for observation, O1 and O2, all the way to OM. And these assume values in a set, let's call it capital O. And in the example here, I made it up, but in practice, usually this is indeed some sort of vectorial data, these observations. Right? So you can think of this as each of the observation variables is actually a d-dimensional vector. And okay, so now we have two random variables. When we begin talking about Markov chains, we approached the topic from the perspective of graphical models. Again, in math textbooks, that is usually not done this way, but we did it anyway because we'll do it again right now. Right? We approached the idea of Markov chains from looking at graphical models, and now we approach the idea of hidden Markov models from looking at graphical models, and you will see this is an immediate extension. So the graphical model underlying the idea of hidden Markov models is the following. Graphical model is, well, we have these state variables as we had when we were talking about Markov chains or Markov models. And since the name is very much resembling Markov chains, Apparently, we are again talking about state transitions here. Chains like that. And now the additional thing is that for each state, we have another random variable for x1, O1, and for x2, we have O2, and all the way up until xn, where we have On. And this graphical model, again, immediately indicates how we would have to factor probabilities when we are talking about hidden Markov models. Because apparently, just as in the case of Markov chains, we have that the states are chained like that. So basically, that is to say the future is independent of the past given the present. This carries through to the Markov model, the hidden Markov models here. But in addition, we also have that each observation is conditioned on a state. That is it. This is the extension we have. And some more terminology here. These x's, the state variables, are called the hidden or latent variables. You know, we assume that they're there. We assume that the character either is guarding the treasure, or is running for hills, or is returning. But we are not able to see it directly, but when we want to talk about what is going on, we have a set of abstract states in our minds. There could be more, but in our example it's just 3. And we know, well, it has to be in either of these 3 states. But we cannot see in which state it is. This is hidden to us. It is a latent phenomenon of what is going on. So these are hidden or latent variables. And the O's here are the observed variables. This we can see. We can see, there was a transition from that, not between state, but it was going, let's say, going from here to there, and then from there to here, and then from there to here, and so on. So we see the movements, but we don't see the states. Okay. Yeah, this is a hidden Markov model. There we have it. I can stop here. Because given what we have discussed so far, you can take it from here. But of course I will not, because other people have taken it already, so why should you have to figure it out all by yourself? I mean, yeah, it's true. I mean, you could, like, given what we have been talking about so far, it's, okay, I see this. Well, if that is the case, but then this has to be like that. And now you could, if you would want to, develop it all by yourself. There's no magic here whatsoever. This is an extension of the idea of Markov chains. And given what we have learned so far, you can try to generalize your knowledge now. You might run into certain stumbling blocks, so therefore I'm not, of course, asking you to do this. Let's continue our journey together. But seriously, this is just a very, very simple extension of what we have been talking about. In particular, it tells us that this joint probability, what are we talking about here right now? We have a lot of state variables, and we have observations. We have twice as many variables in a hidden Markov model. O1, O2, O2, contrast to a simple Markov chain, we have 2 times the number of variables, because for every observed state, there's also an observed output. Well, now these factors, extremely straightforward. Let's think of it. So, first thing is there is apparently a probability for random variable x1 assuming a certain value. In our case, we have 3 states: guard, run, return, 1, 2, or 3. So x1 can be 1 with a certain probability, x1 can be 2 with a certain probability, x1 can be 3 with a certain probability, right? So first factor here is the probability of whatever x1 assumes as a value. Now then, what other conditional dependencies do we have? Apparently, there's a probability for observing something O1 given x1. This depends on that. So we have times P of O1 given x1. And now we have the rest. It's a beautiful tree. If you sort of flip it somewhat, you see that this is the root node of a tree. This is the left branch. This is the first node in the right branch. This is the left branch of the first node in the right. It's a totally imbalanced tree, but it is a tree. And sort of every element in that tree has the same structure. If we take away this, we have like, you know, this up until we reach the end. So basically, to make a long story short, here we have this product over all the remaining probabilities, and they all are of this structure here. So let's make it a product where t ranges from 2 up to n. We have, first of all, the probability of transiting from xt minus 1 to xt. Too generous with my writing. This is basically to say this transition probability has to factor in, right, into the joint factorization here. And then, of course, for every state, we again have this so-called emission probability. So this probability of observing OT given XT. And there you have it. This is almost all you need to know about hidden Markov models. Sort of simplify things, the hidden Markov model, in its simplest form, contains states and possible observations. So we have to fix 2 sets of variables. And the joint probability of many of these state and observation variables factors like this. And I have to erase it anyway, but so let me erase it in 2 steps. So this is a hidden Markov model, right? And again, the difference to a Markov chain is basically this. You see, now we have a Markov chain. That's all. That's all there is. Well, all there is to it. I'm so enthusiastic about it. Yeah. Straightforward extension. Okay. But this is all good and well. If we want to work with this, right, implement it on a computer and use it for computations to calculate probabilities for, I don't know, being in a certain state given a certain sequence of observations, we have, of course, to think about how to fill these abstract terms and factors here with life. What do they really represent? And so let's look at this in more details. So let's look at the ingredients for, I don't know, parameters of a H and N. There are basically 3 things we have to keep in mind. given the factorization, the conditional probability we just wrote down. But first of all, there are these transition probabilities. Transition probabilities, and that is totally analogous to the case of Markov chains, where we had the probability of being in state I at time t, given that at time t minus 1 we've been in state j, and yeah, up until now I abbreviated this with Pij, and you may definitely continue doing this, but I am switching notation and will call it Aij from now on, because that is how every other text does it. Don't ask me why it's called Aij, but if you read something about Markov models, usually this is called Aij. We have called it Pij so far, but now it gets a different name, but it's exactly the same thing. And in particular, this is again a stochastic matrix. Now that these things are called Aij, the matrix is called A, and it is again a square matrix of dimensions n by n, where n is the number of different states we have. And again, we have that the Aij are larger or equal than 0, and in particular, if we sum over the rows, we have 1, and again, that is different as you will find it in the literature. So I have conceded to the literature by renaming it, but I don't concede with respect to the row matrices. They are an abomination of nature. I consider matrix A to be a column matrix. Right? Again, if you read textbooks, usually those are row matrices, which drives me up the wall. But this is a personal quirk of mine. But as you are my students, you have to follow my lead. Okay. This is, we don't even have to talk about this. Right? This is just as with the usual Markov chains that we already talked about this. So then, what else do we have in a hidden Markov model? Right, so once again, if we have this matrix, you can imagine that we can begin computing with all of this. Right? If we have all these numbers, we can plug them into our computations and actually produce numbers in the end. The second thing are these, and I already said it, so-called emission probabilities. And by that, I mean the following probabilities. The probabilities of a certain observation O given a state I. So assume the state variable has a value of I. Say we are in state guarding the treasure. What is the probability when being in that state to observe a certain activity vector? What is that probability? And yeah, this is what it means. In the literature, it is usually abbreviated. So here's another symbolic definition as Bi of O. So when you see this, you have to read it as the probability of observing O given that we are in state I. This is how they write it, and we have that for I. 1, 2. So for every of the states, we assume there is such a function. Is a function now, right? Because I have not indexed this here. This is in a sense one of these probability mass functions we've been talking about earlier. Conditioned on the state. You can think of this being m different functions. And this is actually obvious from looking at this notation here. This B is a function of O. O is some say vector, and this assigns a probability to this vector. And we have m of them. So these are probability density functions. For every state, there is a probability density function that defines how likely it is to observe a certain vector given that state. For instance, could be a Gaussian distribution. So for every state, there would be a Gaussian distribution, and can be different Gaussian distributions. So it is more or less likely to observe a certain vector in this state than it is in that state. This is the second ingredient. And the third one is this initial distribution. Right? So this is the initial state distribution. That is the very first factor in our factor model. The probability of state 1 being I. The first state in the chain is state guard, state return, state run for health. Right? So in our case, I can either be 1, 2, or 3. What is the probability that if we look at it at the first time of the behavior of that agent, it is currently in this state or in that state or in that state? At the very first point in time we look at it. This is what this is supposed to express, and again, this is abbreviated using pi I. So pi I is an element of a stochastic vector. So we have a stochastic vector pi of the dimension of the number of states we have. And just as with these matrices, pi I has to be greater or equal than 0, and the symbol pi I has to be 1. This is just a fancy way of writing down our beliefs in the truth of the idea that at the first time we look at it, the chain is in state guard, or the chain is in state run for health, or is in state return. Can be in either. It's like more likely probably to be in the state guarding the threshold. Who knows? Can be in any state. But first time we look at it, has to be in a state, and this indicates how likely it is to be in each of these states. Now, with these three ingredients, a hidden Markov model is then said to be a triple lambda. Let me make it beautiful. So lambda is a triple containing a matrix A, a set of probability density functions Bi, and this vector pi. This is a hidden Markov model. Indeed, so seriously, if somebody would give you an m by n matrix that is column stochastic, and somebody would give you an m-dimensional vector that is stochastic, and somebody would give you m functions bi, right? M different functions, then you can build a hidden Markov model. All you need to implement a hidden Markov model is such a matrix, such a vector, and a representation of m different probability density functions. And then you have it. There you go. Yeah, let me finish today with making this more complicated than it has to be. Now that we have thought of the hidden Markov model in terms of not this P of something given something, but in terms of Aij and Bi of O and Pi, this is just a different way of talking about this. We can write down this joint probability in a different way. That is, if we refer to the ingredients of the hidden Markov model in terms of these three things here, we get that the joint probability for an observed sequence of states and an observed sequence of output symbols can be written as, maybe I should like now repeat the way we wrote it first. So G of x1 times P of O1 x1 times the product T equals 2 1 times P of T. So this is how we said we can factor a Markov model like previously, and I will now exactly write this down in terms of these pi's, a's, and b's. So here we have pi, and I'm using this here, of x1 times b subscript x1 of O1 times the product where t ranges from 2 up to n, a subscript xt minus 1 times b subscript xt of ot. Can you see that this is indeed the same? Make it more homogeneous. This here. So remember this, pi is a vector. Right? And x1 is a random variable that can have, in our example, 3 different values, 1, 2, or 3. So if we have pi subscript x1, then that could be pi1, pi2, or pi3. So we have to read these variables here. Actually, mentally, you have to substitute them with a number. So here we have a b subscript x1 could be 1, 2, or 3, given or probability either in state 1, 2, or 3 of this observation. And then we have the transition probability from, at time t minus 1 we are in state 1, 2, or 3, and time t we are in state 1, 2, or 3. So this is again these variables in the subscript, you have to mentally substitute numbers here. And then times the emission density function. That's another way of writing this down. And once again, why would I write it down like this? Because these probabilities of xi, probabilities of O1 given xi, this is good if we want to talk about all of this in a very abstract manner. But these are just placeholders. Right? And if you write a program, then these things indeed contain numbers. Somewhere in your program there is a representation of a vector containing 3 elements. Each of these elements is a number between 0 and 1, and they add to 1. So this is exactly the same, but now in terms of the stuff you would implement on your computer. Okay, and I'll cut it at this point because this is a good point to stop. Otherwise, it's too much for today. Are there any questions? I know that this is fairly abstract and a bit removed from practical examples in terms of games. I mean, I'm trying to come up with these contrived examples of guarding treasures and running for help, and I guess that is good enough. But then again, we are here in master's course, and important thing is that you learn about underlying mechanisms and are able to apply them to practical problems. And for instance, I would encourage you to think about the project we had on Monday where we used self-organizing maps and action vectors and somehow use base stuff to create actions. Think about how that could be expressed in terms of this. I'll not do it for you. I will encourage you to try to do that yourself, by yourself. If you can do that. You actually should be able to do that. And then you'll see, oh yeah, this is another way of dealing with that problem. It may be even simpler. Who knows? Great. So I guess we see each other again on Monday, right? See you then.